Hello students, in this video we are going to start very important topic is calculus of variations. Before knowing what is calculus of variation, let us know who invented calculus of variation. The calculus of variations may be said to begin with new minimal resistance problem in 1687 followed by the Brachistochrone curve problem raised by Johann Bernoulli in 1696. So in 1696, Johann Bernoulli of Switzerland proposed a Brachistochrone problem. It is a least time problem as a challenge to his peers, so invented calculus of variations. First, I would like to tell you that why calculus of variation is important and its applications. Calculus of variation is foundation of classical mechanics. So it is very important for civil and mechanical students. Calculus of variation as its application in solving boundary value problems. It also used in derivation of quaternary. Quaternary is the shape like this. Then it's used in the geodesics of surfaces because the actual thing that we are going to do in the calculus of variation is to find out the path. And what is the geodesic? It is nothing but the smallest path between 2 points. Like in two-dimensional space, the geodesic is a straight line. And in three-dimensional space, geodesic sphere is nothing but the great circle like the equator of our earth. Also, we have hanging chain problems, Brachistochrone problems in calculus of variations. Also, it has its applications in control system to optimize the cost index. For example, if we have a satellite, then it needs certain amount of fuel. So, with the help of calculus of variation, we can actually optimize cost index, and also you can think of amount of fuel required to project to the satellite into particular trajectory. So, these are the some interesting applications of calculus of variation. There are lot of applications, like it is used in intelligent bureaus, also in neural network, machine learning. So it has lot of important applications of calculus of variation. Now we should see what is calculus of variation. To understand calculus of variation, we have to understand functional first. Before that, what is a function? A function is from x to y, mapping from x to y means f of x is equal to y. So for each element of x, there will be a one more element y, that is known as function. Then now functional means it is of mapping from set to the real number. So set of functions to the real number. For element in S, it is giving one real number. Such function known as functionals. And the element S are set, can be represented as f of x, y, y dash. Y is a function of x, y and y dash is also a function of x. Then the set can be represented as in the integral format, integral x1 to x2. Consider all the functions, that is a set x, y, y dash dx. So set of all functions, this is called functional. So integral form like I is equal to integral x1 to x2 f of xy y dash dx is called functional associated with the function f of x, y, y dash over the interval x1 to x2. Evidently, the value of I depends on y and y dash. So roughly, functional is a function of function. You can understand easily like this. In a function, in any function, x is a domain element. In a functional, y of x function is a domain element. Now let us know what is calculus of variations. It is a field of mathematics about solving optimization problem. So optimization means minimization or maximization of the functionals. The methods of calculus of variation to solve optimization problems are very helpful in mathematics, physics and many engineering problems. So it mainly concerns with finding the maximum or minimum value of the definite integral involving certain functions, like definite integral involving certain functions in this way. So what is the difference between, you already studied the differential calculus and just here calculus of variation. So calculus deals with the derivative and integral of the function, like integration of y dx. But here calculus of variation deals with the integral of function containing some other functions. Here we can find the maximum and minimum of or optimization of the function. Here we do that in calculus of variation, we do that maximum or minimum of the functional. That's the difference between a differential calculus and calculus of variations. The basic problem of calculus of variation is to find extremal. Extremal means the curve y is equal to y of x, that is in between the limits x1 and x2, such that the integral of some function f of xy y dash is an extremum. Means we are going to find the curve y is equal to y of x that makes the integral form of the function, that is called functional, is extremum. So the curve makes the integral form of the function is extremum, means minimum or maximum. We require a condition to make the functional is extremum. So that is the necessary condition called Euler's equation. The statement of Euler's equation is, it is a necessary condition for the integral I is equal to integral x1 to x2 function of x, y, y dash with respect to x, where y of x1 is equal to y1, y of x2 equal to y2 to be an extremum is that dou f by dou y minus d by dx of dou f by dou y dash equal to 0. This is Euler's equation. So let's prove this now. So let us take the rough diagram. So in a xy plane, let us draw a curve joining 2 points A and B with the line y at the point x and y2 at the point x2. So this is the curve required. This curve is required, y of x. So to prove the result, let us consider the neighboring curve. This is y of x plus h alpha x. So let y of x be the curve joining the points A x1 y1 and B x2 y2, which makes I an extremum, which makes I an extremum, nothing but maximum or minimum. Extremum means maximum or minimum. You can also call optimization problem, where y of x1 is equal to y1 and y of x2 is equal to y2. So accordingly, we prepared the diagram. So we have joined the two points by the curve, and the point at the point x1, the point y1 is present. At the point x2, the line y2 is present. Now to prove the required result, we need to consider the neighboring curve. So that is let y is equal to y of x plus h alpha x be a neighboring curve. Be a neighboring curve. Joining the same points A and B. So such that alpha of x1 is equal to 0 at A, alpha of x2 equal to 0 at B. That's how the curve was constructed. We drawn the neighboring curve where h is very small. So when h is 0, these two curves coincide, thus making an extremum. So we can say that integral I is equal to integral x1 to x2 function of x, y nothing but y of x plus h alpha x, y dash means derivative of that, y dash of x plus h alpha dash of x. Then dx is an extremum when h equal to 0. So when h equal to 0, both the curves will coincide. So therefore we can say that when h equal to 0, the integral become extremum. For extremum, we take di by dh equal to 0 because it depends on h at h equal to 0, treating I is a function of h. So therefore we can write our result di by dh, differentiating the above equation. So when you differentiate the integral, the derivative become partial derivative under integral sign. So it will become dou by dou h of the function of x, y of x plus h alpha of x, y dash of x plus h alpha dash of x dx. So now we have to apply the chain rule here. Applying chain rule under integral sign, because we have the partial derivative. So here how we have f is depending on x, y, y dash, and this all depends on h. So therefore you can define this as di by dh. This can be written as d by dh is equal to integral x1 to x2 dou f by dou x dou x by dou h. It also depends on alpha, that's why we are using both the cases partial derivative. Next, f with respect to x done, h done. Next, f with respect to y, dou f by dou y, then y with respect to h. Next f with respect to y dash with respect to h dx. But dx by dh is 0. This is 0. Why? Because x is independent variable. X is independent variable. And we know that y is equal to y of x plus h alpha x. From this you can find d dou y by dou h. So it's a partial derivative with respect to h. So it gives us alpha x. And dou y dash by dou h is alpha dash of x. Now substituting these in the above result, we get di by dh is integral x1 to x2, and first term becomes 0 because dou x by dou h is 0, and second term we are substituting alpha x and we are writing dou f by dou y as it is, plus alpha dash of x dou f by dou y dash as it is with respect to x. Next we separate the integrals. Here integral x1 to x2 alpha of x dou f by dou y, keeping one integral as it is. The other integral x1 to x2 alpha dash of x dou f by dou y dash dx. Next, we keep the first term as it is. We integrate the second term by parts. So integrating by parts. So what we get? Integrating by parts, this become, so I am keeping first term as it is, that is alpha x into dou f by dou y dx, and we are integrating the second part by parts, keeping dou f by dou y dash is a first function, so second function. So integration of the second function gives us alpha x. Then apply the limit here x1 to x2. Next minus integral x1 to x2 and writing alpha x as it is, and differentiating the first function with respect to x. So we can write d by dx of dou f by dou y dash dx. Next we apply the limits. Here again I am keeping the first term as it is. And applying limits to here. So when you substitute upper limit, when you substitute lower limit, what you get? It is dou f by dou y dash alpha x2 minus dou f by dou y dash alpha x1, and other integral keeping as it is, that is minus integral x1 to x2 alpha x d by dx of dou f by dou y dash dx. But we know that alpha x1 alpha x2 is 0 from the diagram. So therefore you can write combining now both the integral, remaining both the integral. So between the limits x1 to x2 and alpha x is common there, we get dou f by dou y minus d by dx of dou f by dou y dash dx, and alpha x is common here. But this is what di by dh. But di by dh is 0 and alpha x is arbitrary function. Therefore, so let us taking this equal to 0. Therefore, we can take the result dou f by dou y minus d by dx of dou f by dou y dash is equal to 0. So this is our result, Euler's equation. So this is the necessary condition for making functional to be extremum. It is we also note that alternate form of Euler's equation which is important to solve the problems. One is f minus y dash dou f by dou y dash equal to constant. This is we are using when the functional not containing x explicitly. When the function it's not containing y explicitly, we use the Euler's formula in the format of dou f by dou y dash equal to k. So both are derived, and this is very simple to prove. We know the Euler's equation like this: dou f by dou y minus d by dx of dou f by dou y dash equal to 0. When the function not containing y explicitly, then obviously dou f by dou y become 0. Then what is remaining? D by dx of dou f by dou y dash equal to 0. You can remove this d by dx by integrating. So we get dou f by dou y dash, right side on integration we get constant of integration k. That is what we have the second one. So we are derived Euler's equation, which is very important for exam, and also it is very important to solve the problem of extremals.